go to zeus.slu.se/get. Log in with your credentials and maneuver to the area of interest. Scroll to zoom in. Having found your area of interest, click Draw to begin the drawing of a rectangle. Click and hold to adjust the extents of it. Zoom out with the scroll wheel. Adjust the rectangle if necessary. Go to the Select Data tab, and as you see, everything is in SweRef99TM, the National Coordinate System standard. Activate the product Markhöjdmodell nedladdning grid 1 meter plus resolution, the latest one. Add to order. That's the height map. Then add the orthohoto 4 bands 0.16 meter 2019. That's the orthohoto. Information about the datasets can be accessed by this metadata link. Go to the Review and Finish tab. Make sure that your usage of the geodata is according to these terms. Agree to them and press Go to start your order. Download links will be emailed to your KDH address or the address you have forwarded to. Click to download. Select the archive files and extract them. Open QGIS. Drag in the height data image file into the QGIS window. This will change the projection coordinate system from the international standard WGS 84 to EPSG:3006, and that is the identifier of SweRef99TM, the national standard of Sweden. All good. Right-click on the layer and click Properties. Here we can see, as the unit is in meters, that the raster image here covers 2.5 kilometers in width and height, and we can see the coordinate extents in SweRef99TM. While we are here in the properties, let's go to the Symbology tab and expand the min-max value settings. One can see here to the left that as of now, the image height data is interpreted as being from minus 2.43 to positive 32.66, but this is only an estimation. To get the actual values, make sure to change the accuracy mode to actual. Click Apply, and you will see that the interpreted range is changed. The top height is changed from 32.6 meters to a whopping 43.3 meters. That's almost 11 meters. Click OK to confirm. If you have difficulty in finding your plot in the grayscale height landscape, expand the XYZ tiles entry here and click and drag the OpenStreetMap into your layers pane. Now you can navigate to your area of interest and toggle the visibility to confirm. Add a new shapefile layer with a file name of perhaps crop. Make the geometry type a polygon. Make sure that the projection is the same as the project, SweRef99TM. You don't need to have any field or ID data. Click OK to confirm. With your polygon layer selected, click Toggle Editing to enable editing. And if you don't have these two toolbars, you can enable them by right-clicking on the main menu and checking the boxes for Advanced Digitizing Toolbar as well as the Shape Digitizing Toolbar. Toggling these will enable or disable these toolbar areas. Click Add Rectangle from Center and a Point. Click your intended center of your crop. And when you have the rectangle you intend, right mouse button click to confirm. You don't need to enter an ID, just confirm with OK. Click the toggle editing button again and save. Right mouse button, click the crop layer here, go to properties, change the opacity from 100% to perhaps 15%, and optionally adjust the color to something a little more discernible. Verify that the crop covers everything you need and a little extra. If you need to change it, it is easier to toggle editing, select features by a single click, and delete it. Since you cannot move edges and vertices in an orthogonal manner, but only in a freehand manner. If you only need to move it, you can use the Move feature tool here to move it how you want. Click to confirm and click toggle editing to save your editing. Now you can hide the OpenStreetMap layer. It might be tempting to export the layer immediately by right-clicking on it, go to Export, Save As, change the rendered image, leave it as a TIFF, but this would make the exported image an 8-bit grayscale image, and as you might be aware of, a single 8-bit channel can only contain 256 levels of data values, 0 to 255 in this example. For multi-channel color images, 8 bits are in most cases sufficient. All JPEG images are 3-channel 8-bit RGB images, with one 8-bit channel for red, green, and blue values respectively. This is sufficient thanks to each of these 0 to 255 values are mixed between the 3 channels, in the sense of 256 times 256 times 256, or 256 to the power of 3, producing 16,777,216 unique color values by mixing the values of the red, green, and blue channels. On the other hand, with the single channel 8-bit grayscale image, we are stuck with only 256 values. This would mean that if we have a landscape that is 255 meters high from bottom to top, then the resulting landscape model from such an 8-bit height map could only represent 256 different heights, and as such would produce 1 meter high terraces between each value, similar to what we see here. The solution to this is to make sure that the data is exported as a 16-bit grayscale image instead. In comparison to the 256 values of the 8-bit channel, a 16-bit channel, or 2 to the 16th power, contains 65,536 values, and this is more than enough to retain fidelity to the original landscape. With the previous example of the 255 meter high landscape with the 1 meter terraces, due to the constraints of the 8-bit format, a change from 18-bit to 16-bit would reduce the increments from 1 meter to something like 0.003898, or about 4 millimeters. This is of course depending on the height of the given landscape. A landscape with a larger height range than 255 meters will see the increments increase, and one with a smaller will see the steppings diminish even further. But in most cases, if the increments are in the millimeters or in centimeters, they are not discernible to the eye. To make sure that you're getting the 16-bit data, let us convert the imported raster height data from a 32-bit, as can be shown here, which Rhino's Heightfield command does not support, to 16-bit. But first, let's make sure that we crop the height data. Right mouse button click on the layer, click Export, Save As. Make sure that output mode is raw data. Height map crop. Then, to make sure that it is cropped, choose this option, calculate from layer for the extents, and choose your crop layer. This will enter the coordinates of your assigned rectangle, and to retain pixel perfection, these should not be decimal values. Since it is 1 meter per pixel and 1 pixel per meter, and the coordinates are in meters, they should be rounded, and preferably rounded to include the whole meter. So here with the west, we floor this to 1. With the north, we put it to the ceiling of 4. And to the east, we put it to the ceiling of 2. And to the south, we put it to the floor of 4. No, sorry, of 5. Click OK to confirm. Expand the layer here to see that the height range has been adjusted for this particular crop. We can double click on the layer and go to symbology, expand the min-max value settings and make sure that this is actual. It changed slightly. Okay. We can hide the originally imported layer here, as well as the crop. Now, to make the image that we export from QGIS as smooth as possible, we will utilize the whole range of the unsigned integer 16-bit range. That is 65,536 values, all positive integers. To do this, we will be using a few tools. This is done with a tool found in the processing toolbox. If it is not open, open it via processing toolbox or the keyboard shortcut Ctrl-Alt-T. Alright, in the processing toolbox, go to raster analysis, raster calculator. Before using the raster calculator, we will need to write down some values. Open the properties of the heightmap crop. Go to Information tab. Make sure to write down the extents, the width, the height, as well as the origin. Also write down the statistics maximum and the statistics minimum. Thus we can proceed. Double-click the raster calculator to open it. I will paste an expression here that also will be included in the description. At first it might look like nonsense, but we'll select this part and double-click on the cropped heightmap layer to replace that reference. X should be replaced with the minimum value for height. So replace X, both X's, with that. And Y is the statistics maximum. Double check that the expression is valid. Make sure to reference a valid layer. So in this case, the heightmap crop. Click OK to confirm. And we do not need to save this file as it is only used as an intermediary. And when you are finished, you can click Run here. The output will be automatically added to your layer pane. You can expand it and see that all values now have the range of from 0 to 65,535, the full range of a 16-bit channel. If we close the raster calculator, we can also visually check here by toggling the visibility of it that it is identical in grayscale values as rendered as the cropped heightmap. but the actual values have been spread to a much larger range. With this output layer selected, you can go to GDAL here in the processing toolbox, expand it, expand the raster conversion entry here, and double-click on Translate Convert Format. The input layer should be automatically assigned as the output there. And here it is important to change the output data type to unsigned integer 16. It is unsigned, meaning that no negative values are allowed, thus maximizing the positive range to the full 16-bit channel range. It is only integer, that is whole numbers without decimal values. And it is 16-bit, as in containing 65,536 values per channel. This should be saved to a file, since this is the actual exported file that we want. Click Run to confirm. Expanding the layer, we can see here that while the maximum value is retained, the minimum value has been shifted from 0 to 18. This is a loss of precision due to the conversion, but this shift from 0 to 18 only amounts to a loss of precision of 0.0275%, or about 0.3 millimeter per equivalent height meter, and only affects the precision of the lowermost height data. Additionally, these scaled values only determine the smoothness of the Heightfield landscape model. The actual height range will be defined from the original values. As such, we accept the conversion to be able to import it in Rhino. In Rhino, enter the command Heightfield. Navigate to where you saved the exported 16-bit file and select it. With the command activated, you are requested to enter the first corner. This corresponds to the minimum extents that you wrote down earlier. So this is the minimum extents. These are actually the maximum extents. So copy these, go to the Rhino viewport, and Ctrl V to enter it. If you input the second corner coordinates in a way which Rhino does not expect, or if you have the cursor towards a direction which is not intended, this can lead to some very weird rotations, scalings, and positions of the height field, so it is most reliable to simply input the minimum extents coordinates for x and y, like we previously did, and then to input the length, which is the same as the width of the image resolution, as the image resolution is 1 pixel equaling 1 meter, since this data set has that resolution. So we'll go back to what we wrote down, and we'll see that the length is 551. So we'll input this 551 as the length, make sure that the rectangle is projected in this way and not another way. Click to confirm. Now we are asked to define the settings for the height field. The number of sample points can be defined as any amount, but should the number of sample points be beyond the pixel resolution of the height map that we are using, no additional data can be used. So the practical maximum amount is the resolution of the height map that we import. So here we have 551 times 409. 551, 409. The height should be very carefully calculated from the statistics maximum minus the statistics minimum. So in this case, we got 43 points there, minimum, maximum minus the minimum amount, which turns out to be 37.27999999. And here you have the freedom to determine your tolerance, and here we found it reasonable to round up to 37.28 meters, which is accurate to the millimeter, but not to the micrometer. By having set image as texture checked, you will create a material which has the imported height map as the color texture. which can be handy for future manipulations. And here you have 3 different methods, and this option interpolates the surface through samples, does precisely what it says, and is both faithful to the original height map as well as generating a surface brep. Click OK to confirm, and you should save your model before proceeding, since this is a strenuous operation. Alright, expanding the perspective viewport and moving in, we can see that this is a very high density surface with control curves very tightly distributed, only 1 meter apart. If we change to render display mode, we can see that the grayscale height map is imported also as a color texture. It is interpreted as 8-bit, even though it actually is 16-bit, but since it is rendered as 8-bit as a color texture, not as the basis for the height field itself, it has these gradient errors. But this texture is solely used for us to, for future operations, determine whether correct texture mapping has been applied or not. More on that later. Click the landscape, move it up precisely or rounded to a reasonable amount. The minimum value here for the Z height, so 6.02, and then we should have complete concordance with the actual landscape. We can check this if we go to shaded display mode, and since this builds upon a tutorial used for generating landscapes from height curves exported from DP field map, we can check here if they are equivalent, and we can see here that they are corresponding with each other very well. Thus we can assume that we have achieved what we want. We'll hide the landscape of that tutorial. And we can see here that this landscape model is very high density in terms of control curves. I think that if we change to rendered, or perhaps to Arctic instead, we can see that it's a lot of details which might actually be better not accentuating in such a detailed resolution. Thus, we can change back to shaded, select object, create a new landscape sublayer called Heightfield from heightmap underscore high poly, since this has a lot of surface information, an excessive amount. We right click on it and change object layer, which will change all selected objects to this layer, and then we can hide it. We'll redo the Heightfield command, use the same image texture, and for the first corner we take the minimum extents coordinates again, and for the second corner, or actually the length, we input 551 and click to confirm, and perhaps we can choose roughly half of this, so perhaps 275 and 205. Click OK to confirm, and we can save before running it. Here the control curves are far less dense, while still retaining much detailing of the curvature of the landscape. We can determine that this is an adequate amount. We create another landscape sublayer called Heightfield from heightmap medium poly. Select the landscape, right mouse button click, and change object to layer. And actually, before going forward with this, we can actually right mouse button click on this layer, which the landscape Heightfield map has been just assigned to. We can duplicate layer and objects, and we can assign this the name of original height field from heightmap underscore bounding box, or BB perhaps. We can move this up 2 steps. Make sure that this works properly by disabling the visibility of the medium polyheight field and then as the copy, and we see that this is properly here. And then we can click on this and type in bounding box. Press enter to confirm, and now we can actually delete this copy. It is already represented by the medium poly layer there. So we'll delete that, but keep a copy of the bounding box. This is to make sure that we have a faithful representation of the texture coordinates that the height field is representing. And since we had an active layer which differed from the intended layer, we can change the object layer there and hide it. Alright, because when we change the display mode to render, we can see here that the texture mapping, that is the projection of the texture onto the surface, is perfect here. But when we change this, when we extrude this surface, or when we crop it, so perhaps not when we crop it, but after we have extruded it and made it into a closed poly surface, it will have other texture coordinates generated for it, which will differ from the original ones, and we want to retain those. And with the help from this bounding box, we make sure that we have these x and y coordinates for easy remapping of the texture coordinates. I see that I forgot to move up the medium poly as well as the duplicated copy of this then. So I'll select both of them, click here, 6.02, confirm, enter, and now we can hide those again. Or actually just the high poly. Now we can make the landscape surface model conform to our final crop that we intend. Since this is building upon a previous tutorial, we already have an intended crop here. Otherwise, you can create a rectangle. We make sure that this is visible. We click on our landscape here. Control-Shift-S to activate the split command, and click on the curve and press space or enter to confirm, and your landscape surface layer will be split in two. Hold Control and click on the interior part, and then click delete the outer parts. And now we can hide the rectangle, and now it is most pedagogical if we show in the rendered layer what happens when we extrude this downwards. Let's see here if one may see that. Here we have the texture correctly mapped, extrude surface and down, and here we can see that we lost it totally. And this is nothing to cry about as long as we have kept the original height field from heightmap bounding box, because this can be used to redefine the texture mapping later. Alright, I can change back to shaded, and we'll create a plane on the Z0. We'll split this again with the Z0 plane, and we'll control click the upper part, delete the lower part as well as the plane, and cap this. Very good, it is capped. We can change to rendered again. Click on this, make sure that this is reassigned to the height field from heightmap here. With the landscape model selected, click on the material tab here, and click use a new material. Use a new custom material. As the color texture, assign your 16-bit heightmap. Here we can see that the texture is applied to the top surface here, but that the texture coordinates have been corrupted. This can be easily fixed by clicking on it to select it, go to the texture mapping tab, click apply planar mapping, and then to temporarily hide the height field landscape model and instead show the bounding box. And then it does not matter if it's the upper or the lower part, since we'll be only using the X and Y coordinates, but take this corner and the other corner and confirm that this is a UV texture coordinate map, since we do not have any information for the Z-axis or the W-axis. Click UV. And now we can hide the bounding box and show the height field again. And we can see that it is correctly mapped. When evaluating the topology in the Arctic display mode, one can see that the results are actually quite subpar. But this is only because the viewport meshing for brep objects is not according to our standards. To remedy this, we can simply make an explicit mesh version of the brep landscape model by using the command mesh with it selected. The difference between breps and meshes in a nutshell is that breps are mathematical representations of geometries which can be defined as control points, curves, mathematically describing properties of the geometry, while meshes are objects constructed, explicitly or implicitly, purely of collections of flat triangles, which might be showing as rectangles, but those rectangles are only two sets of flat triangles, which makes them easy for the computer to render. Having created an object in wireframe mode, where no viewport preview meshes are created, upon changing view mode from wireframe to shaded, one can see here very briefly in the command prompt that it's actually created these meshes. One can extract this viewport mesh by typing the command extract render mesh. Select last. So here we have the brep defined by the perfectly mathematical curves, defining its radius and diameter, as well as the viewport mesh that is automatically created when viewed in a shaded viewport. When we change to rendered, only the viewport mesh is showing. For complex surface objects, such as our landscape, the viewport meshing setting is too low for our standards, producing jagged edges and artifacts which are not defined by the brep model, as shown in the shaded viewport. To fix this, we can generate an explicit mesh version with custom settings, instead of relying on the automatically created implicit one. Select the landscape model, type mesh. Here the most significant setting is the maximum angle one. Since a mesh consists of purely flat triangles, or rectangles consisting in turn of two perfectly flat triangles, surfaces with significant curvature will need to consist of many triangles to resemble the original geometry, at least in the areas where the curvature is the most significant. The maximum angle setting defines at which angle the highest allowed difference between the original curvature and the triangles of the mesh is allowed. 12 degrees are usually enough to evoke a perception of smoothness, but if jaggedness is discernible, then 6 degrees just might do it. You may preview by clicking preview, but this is seldom too obvious, so you can click OK. Type select last and temporarily move it to the side to give it a glance. When changing display mode from shaded to Arctic and looking here at the areas of artifacts, we can see here that with our custom settings, these are not reproduced. Instead, we have a smooth landscape model, as we expect. I'll click Ctrl Z to undo the movement and instead create another landscape sublayer called Mesh from Heightfield. And right mouse click and change object layer. I'll disable the viewing of the Heightfield brep, and thus only our mesh is showing. But changing to rendered, no, actually we can see here that for the mesh, it actually retained the texture coordinates. If it would have lost its texture coordinates, we could do as we did before, go to texture mapping, apply planar mapping, and when that is active, show the original bounding box of the texture coordinates imported, and that would have solved it. But this was perfect from the start. Having verified that the texture mapping is correct for the mesh model as well, we can easily change the texture that is now a height map to an actual orthophoto. To do this, let us go back to QGIS. Navigate to the orthophoto that you downloaded previously and click and drag the TIFF file into the QGIS window. Show your crop layer again so you see what you intend to export. Click on the imported layer, go to export, save as. Make sure that you output this as the rendered image instead of the raw data, because the raw data consists of 4 channels, where the 4th channel, the alpha channel, consists of infrared values, and those you do not want to be interpreted as alpha values as in transparency. So make sure to select the rendered image mode here. Assign a file name, ortho photo crop, save, and as previously done, make sure that you calculate the extents from the crop layer and that you make sure that these are integers by going to the floor of this 1, to the roof of ceiling of this 4, to the ceiling of this 2, and the floor of this 5. You can see that the pixel resolution here is far more than 1 pixel per meter. It's actually 0.16 meters per pixel. But it's still important that you have the same coordinates as the crop as you did for the height map for it to be as properly as possible be projected in an equivalent manner. All right, click OK to export it. And you see here that there is a slight difference between the 2 projected images, and that is because the one that we exported now had its extents at integer meters, while its actual resolution was 0.16 meters per pixel, which means that there can be a misalignment of such a proportional pixel. All right, this has already been exported, so just navigate to it. Go to Rhino, click on the colored texture link here. Click on the 3 dots to browse for another file. Select the orthophoto. Make sure that you disable the use of an alpha channel. And gamma should be 1 for this particular image for it to render correctly. All right, and now you see here that you have your landscape model from the height map generated and textured with the orthophoto. And you see that there are some jittering and some flickering, but that is only because you have used such a high resolution texture for the color texture. And it is only in the preview mode here. If you actually go to render and click render, you will see that the rendered texture quality is precisely as described. So do not fret if you see this jittering as well. All right, that is all for now. We have successfully generated the height field from a height map downloaded from SLU Geodata extraction tool, and we have assigned an orthophoto as the color texture to it. Things can be much improved and refined, but here we have it. If you have been following the previous tutorial, then it can also be interesting to go to Arctic mode here and to actually compare all the different models that we have generated here. And then here we have the mesh from Heightfield, and we can see that when it comes to the Heightfield from heightmap, they are pretty much identical. Display options uses the object's color, and then we can assign different colors to all of these. Here you can see that the overlap between these are very similar. Keep on using the mesh here as to see if we use the drape here. We can see that the drape is generally lower, but for the curve, for the most steep parts, it actually protrudes upwards. But we can see here that moving half a meter upwards make them comparable, but not identical in any case. I'll undo that. I'll hide the drape here, and then we can show it the patch, and we see that the patch is actually quite similar for some areas, but not definitely all. Let's see here, we can change the layer color here so as to change the object color. And here we have the infamous high point as well, which is not in the height map data and not in the height curve data as well. We can see here if this can have a dark blue hue. You can see that as here we have overlap for some, if not most parts, but some parts have significant changes. Perhaps due to the difference in years of capturing the data with the area laser. All right, you decide yourself which one you prefer, and a side bonus as well is that if you go to, as an example only, the surfaces from curves, if you change this back to black, and then if you select all of these, of course, all of these, go to texture mapping, apply planar mapping, and do as you did previously, temporarily disable the showing of the actual geometry, and then showing this bounding box of the imported height field, and then confirm it as a UV mapping, and then showing it again, selecting everything again, and then assigning the material. And now I just guessed that it was this custom one that we made previously. It is shared by one or more objects. So let's see if it was the correct one. Yes, I think it was. So you see you can apply the same texture mapping for any object positioned correctly, which makes for some pretty interesting results. Alright, that was only a bonus. Thank you for your time.